In example 1, say we want to find our Thevenin equivalent for the circuit below using node voltage analysis. As we see, we have a 125 volt source connected to a 50 ohm resistor, which is connected to a 2 amp current source and a 200 ohm resistor. This circuit is connected to terminals A and B, which may be connected to circuit B. To determine our Thevenin equivalent using node voltage analysis, we will employ our standard 4-step procedure. Step 1 is to assign N nodes and leg currents. We assign node C between our 125 volt source and our 50 ohm resistor, and node A spans the right hand side of our 50 ohm resistor, the top of our 2 amp current source, and the top of our 200 ohm resistor, whereas node B spans our bottom portion of the circuit network, the negative terminal of our 125 volt source, the outlet of our 2 amp current source, and the bottom of our 200 ohm resistor. And we will designate node B as ground. We have I1 exiting our voltage source into our 50 ohm resistor, and we have I2 exiting node A running down through our 200 ohm resistor towards node B. Step 2 is to assign our voltage potentials consistent with our passive sign convention, such that V1 is applied to our 50 ohm resistor as such, and V2 is applied to our 200 ohm resistor as such. Step 3 is to apply N minus N sub C minus unity KCL equations at our non-zero nodes, such that we will apply it at A, for node C is specified. Applying KCL at node A, we have I1 entering is equal to 2 amps plus I2 exiting. Step 4 is to apply Ohm's law in terms of our node voltages, where we'd have I1 expressed as VC minus VA per 50 ohms, where VC is specified as 125 volts, and this is equal to 2 amps plus I2, where I2 is VA minus VB per 200 ohms, where VB is equal to 0, for it's prescribed as ground. We note that VA minus VB, i.e. the voltage potential across our current source and 200 ohm resistor, is our open circuit voltage. Since VB is equal to 0, we know VA is equal to our open circuit voltage. Now we can solve for VOC from our KCL equation. Making our substitutions, we have 125 volts minus VOC per 50 ohms is equal to 2 amps plus VOC per 200 ohms. Or our open circuit voltage is equal to 20 volts. Now, we have to find either our short circuit current or our Thevenin resistance. We will proceed by finding our short circuit current, and to do such we will short terminals A and B and apply KCL at our top nodes. In doing such, we have I1 entering node A, and then we have 2 amps plus I2 plus ISC exiting node A. Now we note that I2 will be 0, for no current will go through our 200 ohm resistor, for it can follow our short circuit. Thus, our KCL equation reduces to I1 is equal to 2 amps plus ISC, our short circuit current. Now we can apply Ohm's law once again in terms of our node voltages, where I1 is equal to VC minus VA per 50 ohms, where VC is equal to 125 volts, and VA is now equal to 0 due to our short circuit, for A is connected to B, which is ground, via our short circuit. I1 thus is equal to 2 amps plus ISC. Since our left-hand side is expressed in terms of knowns, our short circuit current can be solved for as 0.5 amps. Therefore, we can calculate our Thevenin resistance as our open circuit voltage per our short circuit current, which is 20 volts per 0.5 amps, which is equal to 40 ohms. Now there's an alternative way that we can determine our Thevenin resistance, and that is to open our current source and short our voltage sources, and we will look into the circuit, i.e. we will look between nodes A and B and determine our equivalent resistance that circuit B would be experiencing, i.e. this would be synonymous with applying an ohm meter to terminals A and B. In doing such, we short our voltage source and open our current source such that we have a 50 ohm resistor now in a parallel configuration with our 200 ohm resistor, such that our Thevenin resistance is found to be 40 ohms, which is what we found previously. Thus we have a complete description of our Thevenin equivalent circuit.